In mathematics, analytic combinatorics is one of the many techniques of counting combinatorial objects. It uses the internal structure of the objects to derive formulas for their generating functions and then complex analysis techniques to get asymptotics. This particular theory was mostly developed by Philippe Flageolet, and is detailed in his book with Robert Sedgwick, Analytic Combinatorics. Earlier contributors to the key ideas and techniques include Leonhard Euler, Arthur Cayley, Srinivasa Ramanujan, George Polya, and Donald Knuth. After Flageolet's death, Wojciech Szczepankowski is largely responsible for further developments. Together with Jacek Ciszon and Paweł Hitchenko, he created the Polish school of analytic combinatorics. Classes of combinatorial structures. Consider the problem of distributing objects given by a generating function into a set of n slots, where a permutation group G of degree n acts on the slots to create an equivalence relation of filled slot configurations, and asking about the generating function of the configurations by weight of the configurations with respect to this equivalence relation, where the weight of a configuration is the sum of the weights of the objects in the slots. We will first explain how to solve this problem in the labeled and the unlabeled case, and use the solution to motivate the creation of classes of combinatorial structures. The Polya enumeration theorem solves this problem in the unlabeled case. Let f be the ordinary generating function of the objects. Then the OGF of the configurations is given by the substituted cycle index. In the labeled case, we use an exponential generating function g of the objects and apply the labeled enumeration theorem, which says that the EGF of the configurations is given by we are able to enumerate filled slot configurations using either PET in the unlabeled case, or the labeled enumeration theorem in the labeled case. We now ask about the generating function of configurations obtained when there is more than one set of slots, with a permutation group acting on each. Clearly the orbits do not intersect, and we may add the respective generating functions. Suppose, for example, that we want to enumerate unlabeled sequences of length 2 or 3 of some objects contained in a set X. There are two sets of slots, the first one containing 2 slots, and the second one, 3 slots. The group acting on the first set is, and on the second slot. We represent this by the following formal power series in X, where the term is used to denote the set of orbits under Gn, which denotes in the obvious way the process of distributing the objects from X with repetition into the n slots. Similarly, consider the labeled problem of creating cycles of arbitrary length from a set of labeled objects X. This yields the following series of actions of cyclic groups. Clearly we can assign meaning to any such power series of quotients with respect to permutation groups, where we restrict the groups of degree n to the conjugacy classes of the symmetric group, which form a unique factorization domain. This motivates the following definition. A class of combinatorial structures is a formal series where is the set of primes of the UFD, and in the following we will simplify our notation a bit and write e.g. for the classes mentioned above. The Flageolet-Sedgwick fundamental theorem. A theorem in the Flageolet-Sedgwick theory of symbolic combinatorics treats the enumeration problem of labeled and unlabeled combinatorial classes, by means of the creation of symbolic operators that make it possible to translate equations involving combinatorial structures directly into equations in the generating functions of these structures. Let be a class of combinatorial structures. The OGF of where X has OGF and the EGF of where X is labeled with EGF are given by, and in the labeled case we have the additional requirement that X not contain elements of size 0. It will sometimes prove convenient to add 1 to indicate the presence of one copy of the empty set. It is possible to assign meaning to both, and to prove the theorem simply apply PET and the labeled enumeration theorem. The power of this theorem lies in the fact that it makes it possible to construct operators on generating functions that represent combinatorial classes. A structural equation between combinatorial classes thus translates directly into an equation in the corresponding generating functions. Moreover, in the labeled case, it is evident from the formula that we may replace by the atom Z and compute the resulting operator, which may then be applied to EGFs. We now proceed to construct the most important operators. The reader may wish to compare with the data on the cycle index page. The sequence operator. This operator corresponds to the class and represents sequences, i.e., the slots are not being permuted and there is exactly one empty sequence. We have in the cycle operator. This operator corresponds to the class, i.e., cycles containing at least one object. We have or in this operator, together with the set operator, and their restrictions to specific degrees are used to compute random permutation statistics. There are two useful restrictions of this operator, namely to even and odd cycles. The labeled even cycle operator is which yields. This implies that the labeled odd cycle operator is given by the multiset set operator. The series is, i.e., the symmetric group is applied to the slots. This creates multisets in the unlabeled case and sets in the labeled case. We include the empty set in both the labeled and the unlabeled as case. The unlabeled case is done using the function, so that evaluating we obtain for the labeled case we have in the labeled case we denote the operator by, and in the unlabeled as case by. Procedure. Typically, one starts with the neutral class, containing a single object of size 0, and one or more atomic classes, each containing a single object of size 1. Next, set theoretic relations involving various simple operations, such as disjoint unions, products, sets, sequences, and multisets. Define more complex classes in terms of the already defined classes. These relations may be recursive. The elegance of symbolic combinatorics lies in that the set theoretic, or symbolic, relations translate directly into algebraic relations involving the generating functions. In this article, we will follow the convention of using script uppercase letters to denote combinatorial classes and the corresponding plain letters for the generating functions. There are two types of generating functions commonly used in symbolic combinatorics: ordinary generating functions, used for combinatorial classes of unlabeled objects, and exponential generating functions, used for classes of labeled objects. It is trivial to show that the generating functions for an and, respectively. The disjoint union is also simple, for disjoint sets and implies. The relations corresponding to other operations depend on whether we are talking about labeled or unlabeled structures. Combinatorial sum. The restriction of unions to disjoint unions is an important one. However, in the formal specification of symbolic combinatorics, it is too much trouble to keep track of which sets are disjoint. Instead, we make use of a construction that guarantees there is no intersection. In defining the combinatorial sum of two sets and, we mark members of each set with a distinct marker. For example, for members of and for members of, the combinatorial sum is then. This is the operation that formally corresponds to addition. Unlabeled structures. With unlabeled structures, an ordinary generating function is used. The OGF of a sequence is defined as product, the product of two combinatorial classes, and is specified by defining the size of an ordered pair as the sum of the sizes of the elements in the pair. Thus we have for n. This should be a fairly intuitive definition. We now note that the number of elements in of size n is using the definition of the OGF and some elementary algebra. We can show that implies sequence. The sequence construction, denoted by is defined as, in other words, a sequence is the neutral element, or an element of, or an ordered pair, ordered triple, etc. This leads to the relation set. The set construction, denoted by is defined as, which leads to the relation where the expansion was used to go from line 4 to line 5. Multiset. The multiset construction, denoted as a generalization of the set construction. In the set construction, each element can occur 0 or 1 times. In a multiset, each element can appear an arbitrary number of times. Therefore, this leads to the relation where, similar to the above set construction, we expand, swap the sums, and substitute for the OGF of other elementary constructions. Other important elementary constructions are the cycle construction, in which each member of is augmented by a neutral pointer to one of its atoms. Substitution is specified by the recursive relation. In other words, a tree is a root node of size 1 and a sequence of subtrees. This gives we solve for G by multiplying to get subtracting Z, and solving for G using the quadratic formula gives. Another example is integer partitions. First, define the class of positive integers, where the size of each integer is its value. The OGF of is. Then now, define the set of partitions as the OGF of is. Unfortunately, there is no closed form for, however, the OGF can be used to derive a recurrence relation, or, using more advanced methods of analytic combinatorics, calculate the asymptotic behavior of the counting sequence. Labeled structures. An object is weakly labeled if each of its atoms has a non-negative integer label, and each of these labels is distinct. An object is labeled if, furthermore, these labels comprise the consecutive integers. Note: some combinatorial classes are best specified as labeled structures or unlabeled structures, but some readily admit both specifications. A good example of labeled structures is the class of labeled graphs. With labeled structures, an exponential generating function is used. The EGF of a sequence is defined as product for labeled structures. We must use a different definition for product than for unlabeled structures. In fact, if we simply used the Cartesian product, the resulting structures would not even be well labeled. Instead, we use the so-called labeled product, denoted for a pair, and we wish to combine the two structures into a single structure. In order for the result to be well labeled, this requires some relabeling of the atoms in. We will restrict our attention to relabelings that are consistent with the order of the original labels. Note that there are still multiple ways to do the relabeling, thus each pair of members determines not a single member in the product, but a set of new members. The details of this construction are found on the page of the labeled enumeration theorem. To aid this development, let us define a function that takes as its argument a labeled object and relabels its atoms in an order-consistent way so that it is well labeled. We then define the labeled product for two objects and as finally, the labeled product of two classes, and as the EGF can be derived by noting that for objects of size m, there are ways to do the relabeling. Therefore, the total number of objects of size is. This binomial convolution relation for the terms is equivalent to multiplying the EGFs. Sequence. The sequence construction is defined similarly to the unlabeled as case. And again, as above, set in labeled structures, a set of elements corresponds to exactly sequences. This is different from the unlabeled case, where some of the permutations may coincide. Thus for, we have cycles are also easier than in the unlabeled case. A cycle of length corresponds to distinct sequences. Thus for, we have boxed product in labeled structures. The min-box product is a variation of the original products which requires the element of in the product with the minimal label. Similarly, we can also define a max-box product, denoted by the same manner. Then we have, or equivalently, example: an increasing Cayley tree is a labeled non-plane and rooted tree whose labels along any branch stemming from the root form an increasing sequence. Then, let be the class of such trees. The recursive specification is now other elementary constructions. The operators represent cycles of even and odd length, and sets of even and odd cardinality. Example: Stirling numbers of the second kind may be derived and analyzed using the structural decomposition. The decomposition is used to study unsigned Stirling numbers of the first kind, and in the derivation of the statistics of random permutations. A detailed examination of the exponential generating functions associated to Stirling numbers within symbolic combinatorics may be found on the page on Stirling numbers and exponential generating functions in symbolic combinatorics.